Now let's move on to the heart of today's lecture, the IS method of concrete mix design in India. This systematic procedure is laid out in IS 10262 2019. This code gives us a structured approach for selecting concrete proportions rather than relying on guesswork or rule of thumb ratios. The inputs to this method include grade of concrete, exposure condition, required workability, properties of the materials available, and the level of quality control on site. One key concept here, and this trips up a lot of students, is that the design targets the target mean strength, not just the characteristic strength alone. We build in a statistical margin, and of course whatever proportion we calculate on paper are only provisional. They must always be confirmed and fine tuned through trial mixes before being adopted for production. So these are the design data required: the characteristic compressive strength FCK, standard deviation which reflects the quality control at the plant or at the site, degree of workability required and the method of placing, the exposure condition and durability requirements, the type of cement and aggregate size, grading and specific gravity, and finally the water quality along with the admixture type and dosage if one is being used. Now let us walk through the actual design steps one at a time. Step 1 is calculating the target mean strength. The formula is F dash CK is equal to FCK plus 1.65 times S. Here FCK is our characteristic compressive strength, that is the grade we are designing for, and S is the standard deviation based on the quality control data. What is the need of adding this margin? Because concrete strength naturally varies from batch to batch. By targeting a mean strength above the characteristic strength, we ensure that even with normal statistical variation, the vast majority of our concrete still meets or exceeds the required characteristic strength. Yeah, we'll have a quick example. If you are designing an M30 grade concrete and our standard deviation S, which is 5 megapascals, then the target mean strength equals 30 plus 1.65 times 5 S, that is 5, which works out to be 32.25 megapascals. So even though we only need 30 megapascal characteristic strength, we actually design the mix to target 38.25 megapascal on average. So next is to calculate water cement ratio. This is chosen based on two considerations: the strength requirement and the durability limit specified for exposure conditions. Wherever these two considerations give different values, we should adopt the lower, meaning the more stringent water cement ratio. The ratio we finally select must satisfy the specified exposure requirement. Generally speaking, a lower water cement ratio improves both strength and durability, but of course this is subject to maintaining adequate workability. And this is exactly where superplasticizers come back into the picture. They let us achieve the workability we need without having to increase the water content. Step 3 is to calculate water and cement content. We select the water content based on the nominal maximum aggregate size and the required workability. Larger aggregate generally needs less water for the same workability. This water content can be adjusted for changes in the required workability following the procedure laid out in the IS code. If a superplasticizer is being used, the actual water reduction achieved needs to be established through trials rather than assumed. Once we know the water content and we have already selected the water cement ratio from step 2, the cementitious content follows directly. It is simply the water content divided by water cement ratio. We always verify that the cementitious content falls within the minimum and maximum limit specified for durability requirements. Too little cement compromises durability. Too much of cement can lead to other issues like excessive heat of hydration or shrinkage. So next is about aggregate proportion. We determine the volume of coarse aggregate using the tables provided in IS 10262, applying necessary corrections for factors like water cement ratio and the type of fine aggregate grading zone. Whatever volume remains after accounting for coarse aggregate is then allocated to fine aggregate. This entire calculation is based on absolute volume principles, which means we need to account for the specific gravity of every material involved. We also need to account for the volume contributed by any admixtures and for entrapped or entrained air where applicable. Once all these volumes are worked out, we convert them into mass proportions because on-site batching is done by weight, not by volume. Step 5. The trial mix and final proportions. We prepare an actual trial mix using the calculated quantities from our design. We check the slump or workability. We assess cohesiveness and we check for any signs of segregation. We then cast a specimen from this trial mix and verify the compressive strength at the specified age, usually 28 days. Though early age tests can give an indication. Based on the results, we adjust the water content, aggregate proportions, or the admixture dosage as needed. Only once we have achieved a satisfactory workability, strength, and durability do we finalize the mix design. Here is an worked example for M30 grade concrete. We assume a characteristic strength of 30 megapascal and a standard deviation of 5 megapascal, same numbers as before. That gives us a target mean strength of 38.25 megapascal as we calculated earlier. Say we select a water cement ratio of 0.45. If our water content works out to be 160 kilograms per cubic meter, then the cementitious content would be approximately 356 kilograms per cubic meter. That is 160 divided by 0.45. This is purely illustrative. The actual water, aggregate and admixture quantities in a real design must be established from the IS 10262-2019 tables, the actual properties of our materials and confirmed through trials. So never treat a worked example like this as a shortcut to skip the proper procedure. Let us wrap up with the key takeaways from today's presentation. First, the quality of concrete depends fundamentally on the correct selection and proportioning of every single ingredient, cement, aggregate, water and admixtures when used. Second, admixtures are performance enhancing materials, but they require carefully controlled dosage and always demand compatibility checks. Third, IS 10262-2019 gives us the structured framework for concrete mix proportioning in Indian practice. Fourth, durability requirements and workability are just as important as strength. Strength alone doesn't make a good concrete. And finally, always validate our calculated mix through trial batches and testing before adopting it for real construction. So the standard we have discussed throughout this presentation is IS 10262-2019 concrete mix proportioning guidelines, and for durability check requirements we are using IS 456-2000. Thank you.